less than 6 is more volume. And that's all we have left this year is volume. Okay? And so the volume we looked at previously was three-dimensional volumes, and it was cross-sections. Okay? I think this volume is easier. I'll tell you right off the bat. Okay? This is volume using disk and washer methods. And the idea basically is taking a graph and rotating it. Today we're going to be rotating it around either the X or Y axis to make a three-dimensional shape. And finding the volume of that three-dimensional shape. Okay? So, if a region in a plate is revolved about a line, the resultant solid is what we call a solid of revolution, and the line is the axis of revolution. The simplest such solid is a right circular cylinder or a disk, okay, which is where we have our disk method, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. So if we look at this, okay, this region R. This region R is bounded by the x-axis, the y-axis, and then the line x plus 3y equals 6. If you take that and you rotate that about the y-axis, okay, so we're taking this triangle here and rotating it about the y-axis. I don't know if you can visualize it, but here's the visual. This is what a triangle rotated 360 degrees, okay, so this right here is my axis. Rotate that triangle all the way around, it now becomes a cone. Okay, becomes a cone that still has that height of 2 and it still has that radius of 6. Obviously, you know, this is a very basic example. Pictures won't always be that easy, or, you know, the numbers that obvious, I guess. Now, to find the volume of the cone, we could simply use the formula 1/3 pi r squared h. That is volume of a cone if you go back to whatever grade you want to talk there. So if we do 1/3 pi r squared h, let's do the math real quick. 1/3 times pi, r squared is 6 squared times a height of 2. My brain says 6 squared is 36. 36 divided by 3 is 12. Times the 2, we get a volume of 24 pi. Agreed? Hold that thought for later, because we're going to do this same problem later, but by using integration. Okay, so I just kind of want you guys to be there. Now, instead, let's explore the idea of a strip sliced through the region revolved around the y-axis. Remember that x would represent the coordinate of some point P on the graph, and as such is also the length of our strip. When the strip is rotated or revolved around the y-axis, it forms a thin disk. So, you know, with our cross-sections, I would either draw a vertical or horizontal cross-section, right? Same thing here. We're either going to have a horizontal or vertical piece. This is rotating around the y-axis. So if we're rotating around the y-axis here, then the piece, you know, whether you just draw it as a single line like this, that goes from the curve to whatever you're revolving around, which in this case is the y-axis, it's that single strip, or it's basically a little rectangle. Okay? And so now, for what we're going to do, we probably do want to talk about kind of as a rectangle. The idea here is that we have an infinite amount of rectangles, right? That's what the integration does for us. It accumulates and adds up all of those rectangles. These rectangles, okay, take this one little rectangle and revolve it. If you take just this one little rectangle and revolve it, what is my shape here? It's a disk, okay? Thus, the disk method is what we're starting off with today. We'll get to washer method, but we've got to master the disk method first. But it's a disk. Now, that disk has some minute height to it, right? And then it has a radius. Now, if this is a vertical, this is not vertical. If this is a horizontal rectangle, then notice that is a x value, yes? So the idea here that the volume of this disk is going to be, okay, let me ask, what shape is this? It's a disc, but it also, as it has a small height, it's a, what's this shape? A cylinder, yes? And so side note here, what's the volume of a cylinder? That is pi r squared h without the 1/3, right? Cylinder is pi r squared h. Cone has the 1/3. Well, do you see it? The volume of this disk is going to be pi. Instead of r squared, this case, since it's a horizontal rectangle, it's x squared. What's the dy represent?
H.
That's your height. Okay, because it's that change in y. Okay, so the idea here is this cone is created by an infinite number of thin horizontal slices or strips whose sum will create the cone. So you've got slice, 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 and that's what the integral is doing. It's accumulating those pieces. When we talk dy dx, we talk slope. When we talk just, excuse me, when we have the dy here, and what it comes down to is we're going to be talking integrals in a moment, right? And so when we talk dy, I think of change in y. Okay, kind of like delta y. I don't know if you're more familiar with the delta y, but equivalent to that idea. Okay. Now, we could also think of it as integrating the area. Yes. This little piece makes a circle, right? Area of a circle is the pi r squared. And when you integrate the area, then the height comes into play as the dy. And so we are still integrating the area. It's just a disk is that pi r squared piece. Okay? Now, let's put it all together and try to think, is there anything else that I should have written down here? No. I guess I did write underneath here that this is the same as saying pi r squared h. Like that's kind of how that pairs up there. Now, I think I'm going to do example 1 over here because I can. You guys have plenty of room down there. I was just trying to save pages. So write the volume of the cone as an integral on the interval from 0 to 2, and then find the volume of the cone. Now, let's start with v equals. I'm going to keep it basic here, right? When we talk about this, because this is, just like yesterday, a horizontal section, right? We're revolving around the y-axis. We're going to do this in terms of y. Okay? So we're going to do this in terms of y. When you revolve around the y-axis, you're in terms of y. When you revolve around the x-axis, you're in terms of x. Now, we're going to have pi, yes? What is my radius going to be? In other words, here it says x, yes? So if I use, I'm just going to put it in here for a moment. I'll switch it out here in a moment. Okay, so just think it's going to be, well, hold on. How do I do this? X is my radius, yes? But then as part of the formula, it's pi times the radius squared, so x squared. But then, what are we supposed to be doing this in terms of? In terms of y, right? So dy. So do I really want an x in here? No. Just like yesterday. What did we do to find that? We're rotating the triangle around the y-axis, which is going to give us the cone. Okay? iPad is not going to. Nope, wrong way. Still, turn the volume down. There we go. Okay, so I guess what I'm trying to get you guys to go at is here, if we talk pi, I said x, but what is x equal to? What is this that I'm rotating? That right there is the edge of the shape, yes? That's like the outer function. So that means in this case, if it's x plus 3y equals 6, then when I solve that, and I solve that for x, x is going to be 6 minus 3y. So right here, where I had x, that's actually going to be 6 minus 3y quantity squared dy. So very similar to yesterday in that, yesterday I guess we had to more create these. Today it's pretty much going to be what's the function that we're rotating around. And the function I'm rotating around is this straight line. And I'm rotating around and around. Now my values, I haven't got my values on there. Because we're in terms of y, I have to do this in my boundaries are y's also. So how low and high does this go in terms of y? As low as 0. And how high was this? That had an intercept of 2, yes? So my boundaries are going to be from 0 to 2. Now, I have more of a set formula on the next page, okay? But this is always going to kind of be the setup. Now, math-wise, how do we do the math? Still making noise, my turn. Okay. Pi can be pulled out front, yes. What do I need to do before I integrate 6 minus 3y quantity squared? We need to FOIL. Did I FOIL that right? 6 times 6 is 36. 6 times negative 3y is going to be negative 18y. Another negative 18y is going to be negative 36y. Minus 3y times minus 3y is plus 9y squared. And then I can integrate, keeping my pi out front. Integral of 36 is 36y minus 36y becomes y squared, divide by 2, 18y squared, plus y squared becomes y to the third, divide by 3, and it's 3y cubed. Evaluated from 0 to 2. Okay. Plug the 2 in, subtract, plug the 0 in. 36 times 2, 72. 2 squared is 4. 4 times 18 is also going to be 72. 2 to the third is 8. Times 3 is 24. And then what happens when I plug in 0? We get nothing. What do we end up with here?
Mason Yeagley, Waylon and Parker Gerald, please report to the high school office. With Mason Yeagley and Waylon and Parker Gerald, please report to the high school office. Thank you.
Notice, does this answer match the answer of what we found earlier? And it does, doesn't it? Okay. What questions do I need to answer? Or do I need to show the next page and then we'll talk questions?
So, I know you marked up a lot on the
Too much, but yeah.
one, but like, how does the cylinder turn into the cone? Or maybe I'm not. Is that how you're? Is that not how
So
you're thinking
this
about it?
cylinder is one little piece of the cone. So what it is you've got a cylinder here,
Oh,
a cylinder
so
here.
Okay.
It's a stack of cylinders.
Okay. I don't know. Just the picture had it drawn. I was only one, so I was like, okay.
No, so this right here is representing this
that.
one piece.
Okay.
There's going to be, that's just one piece. Like yesterday you had one cross section we draw in, but there'd be one, one on top of
So
another.
that's why you want the integral for the.
Because it's the
Okay.
accumulation. Okay? Okay. Let's continue. Because the next page kind of summarizes a little bit. So when finding volumes of a solid of revolution, it's important to focus on what happens to each individual slice or disk as it is rotated around a line instead of thinking about the total volume. A thin slice or strip can be horizontal or vertical. Now, when we talk about the volume of a disk, okay, it's a cylinder, right? We talked about pi r squared h. Here it's listed as pi r squared w, where w is the width. Pi r squared h, pi r squared w, same idea there. And then, so the volume of the disk, this is what I tried to mention earlier, can really be broken up into the area of the disk times the width of the disk. So I guess I was getting ahead of myself on the other page. But the area, because the area of a circle is pi r squared, right? Times the width or the height, which in this case we used as w. When we go to do this here, when we go to find volume, okay, well, it's going to be pi times the integral, and it's going to be, what's going to represent the radius is the function squared, which is what we did on the other page. We had that, what was it, 6 minus 2x or whatever? Okay, it's going to be that squared. So every time, now this one is, for instance, if you have a horizontal axis, so that's what we just did, right? No. Oh my gosh. Horizontal. Horizontal axis. So if we have a horizontal axis, that's the x-axis, right? Or at least for today it is. So that means we're going to be working in terms of x. Notice this one, it's always going to be pi times the integral. Your radius squared is your function. Okay, how far are we from that x-axis times dx? If it's a vertical axis, which one's my vertical axis? That is my y-axis. So we're going to be, the difference is we're going to be in terms of y instead of x. Now also, as we talk about that, keep in mind, up here, a and b are going to be x's. What about down here? C and d are going to be y values, aren't they? So do pay attention to that. Okay? So let's try some of these. I feel like I'm making this more confusing than it is, so hopefully it gets better here. Set up and evaluate an integral that gives the volume of the solid by revolving the region. And in this case, it is about the x-axis. So, what does y equals negative x plus 1 look like? Has a y-intercept of 1. Where's it going to cross the x-axis at? 1, because if your slope is negative 1, it's going to cross there at 1, yes. And then, so we're going to take this piece here. I don't know. Try that. The piece that's formed, I guess it doesn't say, okay, usually unless they tell you otherwise, you assume the x and y axis. So the piece right here that I'm shading, you can see that fun colored green, that's the piece we're going to take, and we're going to rotate it about the x-axis. Okay, I usually draw that little arrow in as kind of a visual reminder of, wait, which one am I integrating across, or revolving around. So because of this, my rectangle that I'm rotating, okay, that thin strip is going to be a vertical thin strip. And that vertical thin strip, that's the strip we're going to rotate around. And so this is going to be a vertical disc, right? So we're going to rotate around. This is going to be a vertical disc. This is basically going to look like the cone on the other page, but standing on its side, if you will. Okay. When I think about this, this is your y value, but that just means, we're still going to do it in terms of x, but like I was saying yesterday, this is a y value. It's also, my radius. So whether you want to call it y or the radius, I was kind of writing both in my notes. And because I'm rotating around the x-axis, and my area that I'm rotating around the x-axis borders the x-axis, I do know this is going to be the disk method. And that's important to note because later we'll have to be able to distinguish between, do I use a disk method or a washer method. If we butt up against the axis we're rotating around, it's a disk method. Okay? So, let's set this up and see if we can do it. Volume equals. What are we always going to start with when we're rotating? Integral. Okay. What else do we always have to have? Limits. I'll get to those in a moment. What's always going to be part of these? Pi, yes? Now, you can put inside or outside. Okay. Pi, radius squared. Radius is my function. What is my distance from the x-axis up to my line here? Well, it's whatever y is. What is y equivalent to? Negative x plus 1. So it's going to be the function. So I'm going to say negative x plus 1. Because that's my radius, I'm going to square it. And then the height of each of these little discs is going to be represented by dx, the change in x. What are my boundaries? Which one? Okay. Just have to ask just to be safe. Because we're working in terms of x, we're going to use the 0 to 1, specifically the 1 on the x-axis.
I don't think that was very well thought out.
I know. I was like, and it's whatever. It's still an okay problem. But I'm like, I hate when that happens because you can get it wrong and we don't know. So let's just say that they're going to be a little more thought out than that on AP, right? So, okay, what do we do? I'm not going to integrate quite yet, but yes. I personally am going to FOIL. So when I FOIL this out, I have x squared minus 2x plus 1, if I've done my math correctly. Keeping the pi out front, I'm going to integrate now. So pi times 1/3 x cubed minus x squared plus x evaluated from 0 to 1. And you can do this math, right? One-third minus 1 plus 1, and then when I plug in the 0, it's not going to matter, is it? So 1/3 minus 1 plus 1. Final answer of? I'm going to express it as pi over 3. You can say 1/3 pi, that's equivalent. Okay, questions there? Or is it really easy, or are we just lost? Or we're not sure yet. Okay. Ready to try the next one? Okay. This is where, all that pre-calc part of you have to know some basic graphs comes back. This is where you have to know some basics, right? Y equals square root of x. What is that? Top half of a sideways parabola, yes. And then, so y equals square root of x equals 0, and x equals 4 are my boundaries, essentially. Well, where are x equals 0 and 4? Here's 0 and there's 4. And actually, I guess I don't necessarily, I mean, the idea is it's that those lines intersecting each other. Okay. And we're revolving around the x-axis. So I'm taking that piece, revolving around the x-axis. Can you kind of visualize what it's going to make? A what?
A donut. Oh, x-axis.
That's why I was like,
Oh, a donut.
I'm not seeing a donut. Where is he getting a donut? What'd you say?
A dome.
A dome? I kind of am almost thinking like a cup, but that's not flat on the bottom. Like if you look at this as the bottom. But realize when you're rotating it, this basically there'd be an equivalent piece down here, right? And it's going to be full in the center. Okay. Can we set this up? I guess I should mention we're rotating about the x-axis, so where's our piece? That thin little strip is a vertical piece, isn't it? And that represents my radius. It's also a distance of y. Okay, volume equals what? What's my setup? Pi. Integral. 0 to 4, because we are working in terms of x's, and those are my x boundaries. Then what?
X.
Okay. I'm going to write it as square root of x squared for the moment, just because we're beginners. These are our notes. But I'm not disagreeing with x, right? Okay, are we okay with that setup? We've got the pi. We've got the radius squared, as that's our function squared. The height is our dy. And that's how we find volume of a cylinder. Okay. So this is the same as doing pi times the integral from 0 to 4 of x dx, which does make the math nice and easy. Pi times 1/2 x squared, evaluated from 0 to 4. If I take my pi times my 1/2 and make it pi over 2, and then it's 4 squared minus 0 squared, so pi over 2 times 16 is going to make it 8 pi for my volume. And you have to pay attention because that one was rotating about the x-axis. Okay. Number 4. Y equals x squared, revolve about the y-axis from 0 to 4. So what's y equals x squared? Parabola. Well, okay. Officially it says a parabola. It didn't just say in the first quadrant or whatever, so I drew both quadrants. But here's the deal, guys. We're rotating about what axis? The y-axis, right? If we're rotating about the y-axis, what's going to happen when we're rotating this about the y-axis? Do you really have to have both halves here? No. Okay? If you just had the first quadrant piece versus, in this case, the first and second quadrant piece, it's still going to give that same shape. Which, if you think about it, is really the same shape from earlier, isn't it? Just that one was sideways. Now, on what interval? 0 to 4. What type of interval is that? Those are y's, aren't they? So that is from 0, which is obvious, to 4. So we're saying from there to there, right? So the piece we are rotating is that whole big thing there. And because it is rotating about the y-axis, this time my piece is horizontal, yes? Now, I could draw in, here's the deal, I could draw in that whole horizontal piece, can't I? But when we're rotating that about, it's rotating on top of itself. So we're still only really talking about that piece there as being our radius. Or in this case, since it's a horizontal, it represents x. So whatever x is equal to. And again, is my area that I'm rotating touching the axis I'm rotating about? And it is. So this again is a disk method. This one also. You only know disk method right now, but they're disk methods because they are touching the axis you're revolving around. Okay, did you set up? What did you start off with? Not you're gonna forget the pi, right? Beware, guess what they do on multiple choice questions?
Hide the pi.
They'll give you one answer with a pi, one answer without a pi. Right? So just beware. Okay, what are my boundaries? 0 to 4. What's the inside of my integral? Okay, this is y equals x squared is what was provided, yes? We need the x value. So x is equal to what? Well, if you solve that, x is the square root of y. And so we are doing the square root of y squared times dy. You want to take a guess as to what the final answer is going to be?
8 pi.
Why is it going to be 8 pi? Didn't we just do the same math on the last problem? Technically, this one's a parabola that was a square root function, but the difference is just the same object, but on its side. So, just saying, if you don't want to do all the work, it is the same. We won't talk about the fact that I worked through it and didn't realize it until the end, but I was like, wait, this is really looking familiar. So, pi times 1/2 y squared from 0 to 4. Pi over 2 times 16, which is 8 pi. One more on this page. Number 5. Y equals e to the x, revolve about the x-axis from 0 to 2. Can you visualize that graph without graphing on your calculator? I need you to be able to. I don't like how I drew that, but remember when we learned it, it runs as an asymptote along the x-axis, yes, and then goes infinitely up. Now, do I need all of that for this graph? No. I'll leave a little bit there just for the visual, but runs exponentially up. This is an exponential growth graph also. Runs along the x-axis as an asymptote. On the interval from 0 to 2, it did specifically say about the x-axis, right? So we're working in the x-axis here. If it's saying from 0 to 2, that's what I tend to do. So I go to 2 and I'm drawing that line, because essentially it's the line x equals 2 that is blocking it off. Okay. Because, let's see, what are we doing? We're rotating about the x-axis, so my strip is what? It's a vertical strip, right? So this is going to be a vertical disc. Not that it matters, but this represents my radius, or it's a vertical value, so it represents y. So we're going to have y equals whatever. Okay, what do you have set up? I got v equals is what I have set up. Pi and an integral? Okay. They told us the interval, 0 to 2. Almost. Okay. So it's e to the x, quantity squared, dx. Now, in order to be successful here, you need to understand what is e to the x quantity squared. Nope. What do you do with a power raised to a power? You multiply. So e to the x raised to the second, x times 2 is 2x dx. And this is where, if it's a calculator active problem, you can just plug that bad boy into the calculator and you don't have to worry about it. You can do e to the x, put that e to the x in parentheses, square it, but we don't have that option here. Okay, we ready? Let's see, how confident do we feel today? Can we integrate that? Do we need to use substitution? And here's what I think, okay? I think if I was going to take the derivative, if I'm going to take the derivative of e to some power, right? It's e to some power times the derivative of some power. The derivative of 2x is 2. Now, I'm not trying to take the derivative, though. I'm trying to integrate. So what do I do to compensate or balance out that 2 that would be part of the derivative? You do a 1/2 out front instead. Now, if you're saying, yeah, no, not happening, Mrs. Sargent, well, then plan B here, we're going to do a U substitution. Might not hurt some of you to see this visual. Some of you are saying boring, but oh well. U equals 2x, right? Because I'm going to set this up so it's e to the u. If u equals 2x, du equals 2 dx, right? Now, look at your pieces. This is going to be u, right? So it's going to be e to the u. Do I have a 2 dx as part of the problem? I don't. So if I divide this 2 over, 1/2 du is going to be equal to dx. So the dx can be replaced with 1/2 du. Now, so for the moment, it's e to the u du. Whoops. What am I forgetting? Well, how do I want to do this? I guess what I need you to think is it's going to be 1/2 e to the u du. But here's the deal. I don't really want to switch over into u's. I could. And if I switch over into u's, just realize I can't use 0 and 2, right? So if we now integrate this as is, pi, 1/2 e to the u, what's the integral of 1/2 e to the u? 1/2 e to the u. I'm going to go back to my x's, though. And so if I go back to my x's, this was probably not the best way to show it in retrospect, but if I go back to my x's, it's pi times 1/2 e to the 2x, evaluated from 0 to 2. Because I guess what I'm kind of saying is I'd like you to get to the point where you don't have to use u substitution on that one. You can do that a mental u substitution. I'm not saying that on all u substitution, but this one's a more basic one. Okay? However, my point showing this is if you need to write it out, write it out. Let's see, what do we have? A pi over 2. And then what? E to the 4th minus e to the 0. What'd you give as your final answer? Pi over 2 times what?
E to the 4th minus 1.
E to the 4th minus 1. Does 0 matter here? That 0 matters this time, doesn't it? Now, fun fact. This is a good AP answer. This is a good AP answer. Pi times e to the 4th minus 1 all over 2. That's a good AP answer. I mean, those are all free response options. Okay, now, what do we usually do? We probably do something like that, don't we? However, AP, as long as you get it to a number form, as long as it's all numbers, there's no more, it's something that I can plug in all on the calculator and find out its equivalency, it's good. Okay? So this, not good, because I don't have all numbers. I still have to, actually do the evaluation. But anything after you plug those in, you can leave it in that most rawest form that we've always been taught not to do. Right? The one that's roughest for me to leave it in because I'm like, yuck, no. Okay? Now, I have specified several times today, and like I did on this one, we are rotating here about the x-axis. Where did my area that we were rotating about butt up against? It's touching the x-axis, right? When it's touching where you're rotating around, that makes it a disk method. Now we're going to talk about the washer method. I'm not talking about a washer machine. I'm not talking about a washing machine. I'm thinking about nuts and bolts and washers. What do you know about that type of washer? Has a hole in the middle, yes?
Can we call it the donut method?
I like them.
I knew that was coming from Jacob. I saw that coming. Okay, so officially in calculus, it is the washer method. I get the idea when you say donut. Now, why can we technically not call it the donut method? We need something a little flatter, right? But I get where you're going with that. Okay, now washer method can also revolve around the x or y axis, and that's the deal. This time it's going to be a washer or a ring. And so this time we're working with two radiuses. We have an outside radius and an inner radius. So often in calculus, the larger outer radius is capital R, and the smaller inner radius is lowercase r. With that in mind, the idea here is you're subtracting your radiuses, but you're not just subtracting your radiuses to come up with one radius, because it's going to vary at each part of the function. But we're going to do the idea of the area of the larger circle, so the outside circle, minus the inside area. In other words, if I was trying to find the area of this washer, how have you been taught years ago to find the area of this washer? You find the area of the outside circle, right? And then you subtract out the area of the inside circle that's missing. That's what we're doing with washer method. Okay, so you'll see there pi capital R of x squared, so the big radius function squared, minus pi times little radius x squared. 99.9% of the time you see the pi already factored out, right? And so it's going to be pi big R squared minus little r squared. Okay. Whereas here, R of x is outer radius. Little r of x is inner radius. let's see. On this particular problem, the sample that is drawn up, this is an example of rotating about the x-axis. And I get it, it's really hard to visualize these problems. Okay? But the idea is if you take this piece and you're rotating it around, yes? It's this strip here that is rotating out and around all the way around. And so that piece rotating out and around, there's going to be a hole in the center here, isn't it? Thus, it's the washer. Okay? I don't know if you can tell what this picture is, but that's what this 3D picture is supposed to be.
Volcano.
Wormhole.
I had.
Interesting definitions. Very. Yes.
So when this rotates, is the shape continuously rotating on itself? I guess I'm kind of confused on the concept of it rotating. And
I mean-
making the actual shape.
Technically, if it rotates once, it makes the shape. Because if you take this all the way around 360 degrees, I mean, technically the rotation is 360 degrees, is what we're doing here. If I take this all the way around, come out front, go down, go out back, it's going to connect to itself. And so it makes one shape, yes, one figure.
So like, where is its point of rotation?
At the axis?
In this case, this one is, you'll always be told what you're rotating around. So this one is, it's being rotated around the x-axis. So, like, and that's why you can see, like, this piece here, when it rotates, it's this piece down here. Okay? I don't really see the inside piece that I can draw there. You know, but the idea is, what? There was an inside piece right here. Well, that's down here.
Okay, I was just like wondering where.
Okay? And so this is making a hollow object. I mean, this right here is not hollow. Okay, this is a, you know, actual an object. You know, that's filled in object. But there's a hole in the middle, the donut part, okay, that is hollow. Okay? When you do this, you're always going to, if I'm rotating around the x-axis, which is my farther out one, so in this case, that f of x function is my farther out one, and that's going to be my big R. Whereas, which is my closer one to the axis of rotation, and that's going to be g of x, which is my little r. So when I go to set that up, it's going to be the pi times f of x squared minus the g of x squared. Okay. We have similar formulas as to what you saw earlier. Horizontal axis, which is your x-axis, is still in terms of x. Vertical axis, which is your y-axis, is still in terms of y. Notice, x, x, x. What are a and b? Those are x's. Y, y, y. What are c and d? Those are y values, right? And we've talked about this, but I'm not sure I really have time to put it into play, do I? Especially because we have to draw the graph for number 6, so that's not happening. Okay. So you can do disk method in homework. Washer method you could try, I mean, you know, but we'll definitely come back and do a few washer examples tomorrow. Sound good?